Ready? Yeah, so I got to do a little condensation to sort of figure out things. So first, I'm just going to simplify the battery. So I get this, I'm going to do this, and then that. And then finally, if I simplify it, so again, simplifying the battery, I'm just going to get this. Does that make sense to everyone? These are parallel, so I just add them. And then C1 was how much? 4.5 microfarads, and then these two added up were 9. So this is 9 microfarads. Now I add on inverse, so that's 1 over 4.5 plus 1 over 9, which is 2 over 9, which is 3 over 9 is 9 over 3, and so this is 3 microfarads. Right, so let's do that slowly. 1 over 4.5 plus 1 over 9. So multiply this by 2, and you get 2 over 9. Add those up, you get 3 over 9. Invert them, you get 9 over 3. That's the total capacitance. Are we good with that? That's that standard inverse model. Okay. And then now, it's pretty straightforward how we can do this. Is there a way to do this? Electric, yeah. Yeah, C2 was how much? One was 4, one was 5, right? 5. Okay, so this is 5 microfarads, and this was 4 microfarads. Yeah, and because they're parallel, I can just add them. Very good. Okay, so here, I know what's the battery? 3 volts. So then, since C is Q over V, Q is C times V, so Q is CV, which means 9 microcoulombs of charge. So connected to both plates, there has to be 9 microcoulombs of charge, which means here there must be plus 9 microcoulombs, and here there must be minus, connected on this side must be minus 9. Does that make sense? Now, doesn't it make sense that the bigger one's going to have more charge? So then that means this is going to be negative 5 microcoulombs. This one's going to be negative 4 microcoulombs. The other day on Friday, this is what I was trying to do, but I didn't draw a parallel connected to this. I drew a single, and that's why my brain was short-circuited. Right? It has to be the same charge on both sides of the battery, but there is a way where it can be split up, right? And then everything's balanced, everything's smooth. Yeah.
Why is that negative?
What pole the battery is it connected to?
The pole of the battery.
Uh-huh. Well, which one is this connected to? There, it's why it's negative.
Oh, that capacitor plate is the negative.
But this is positive. And you see this is negative?
Yeah. So
Where the heck did this negative 9 microcoulombs come from?
It has to be
But there's no battery here. How did this pull negative 9 microcoulombs out of the air? It didn't pull them from the air. It pulled them from the other capacitors. Right? That's why these became plus. These didn't become plus because positives went onto those plates. They became plus because we sucked off 5 microcoulombs of negative charge off of this one. That went over to this battery. We sucked off negative 4 microcoulombs here. That went on this side.
Oh, so the 9 microcoulombs goes to capacitors of that battery. Which
Yes. Do you see why we have to invert? That's why we have to invert in series. Because there is no source of charge for the middle. If you have a single capacitor connected to a battery, then like I'm doing double work, right? I'm shoving charges on the negative, and I'm pulling charges off the positive. And when I do that, both sides are kind of like connected to this big source, right? One is connected to the negative source of the battery. One is connected to the positive sink of the battery. So you can get as many charges as you want, and you can throw away as many negative charges as you want. You can get as many electrons as you want, throw away as many electrons as you want. of course, depending on the electric potential of the battery, but you get what I mean. But when we put capacitors in series, like this, in series, this middle section here does not have any way to gain charges, right? So if one side is bigger than the other, there has to be some compromise made. Because just because this side wants, whatever, let's say 20 microcoulombs, the other side might not be able to supply it because it's a smaller capacitance. You see what I'm saying? Right, because a smaller capacitor can't take as much charge. So that's kind of why the inverse is weird. Okay, questions on that part? Okay, well we just did this first. Sorry, I don't know why my brain just went there first. So Q1 we know is 9 microcoulombs, Q2 is 5 microcoulombs, and Q3 is 4 microcoulombs. And then it becomes pretty obvious what to do here, because we just have to use the same Q is C equals CV. So V is Q over C. So what's 4 divided by 4? 1. So this is going to be 1 volt. 5 divided by 5, 1 volt. 9 divided by 4.5, 2 volts. Oh wait, that's 4 volts. We messed up, right? Did we mess up?
No.
Okay, now you know. Go ahead, Em. Right? It's parallel. Does this violate the loop rule if we have more volts than our battery has? No, it does not violate the loop rule, because the loop rule, loop means half. So if I leave the battery with 3 volts, I lose 2 here, I lose 1 here, 0 back to the battery. I lose 2 here, I lose 1 here, 0 back to the battery. Watch this. If I go through here, I lose 1, which gives me, let's pretend I started here with 0. I have -1. Now if I go around this loop, when you go backwards through something in a circuit, you reverse that. So instead of losing a volt, I gain a volt, boom, and I'm 0. That's the other trick about the loop rule. Any loop you pick in a circuit has to be 0. Which means, yeah, it's a law. If you go through a circuit, if you go through a resistor with the current, you will lose voltage. But if you go against the current, you will gain. And that's the thing that you're going to want to remember. If you go through an item in a circuit with the current, you will lose voltage. Unless that item's a battery. But if you go against the current, you will gain voltage. Likewise, if you have a battery, if you go with the current from the battery, you will gain voltage. If you go against the current, you will lose voltage. So if you stick a battery in, that happens. All right, there you go. That's that problem.